This call is now being recorded.
Okay, sorry, I could not record earlier, but we discussed about the convective heat transfer. Okay, so on the surface, there are two ways. One is from the circumferential area. So so there can be a heat transfer from this surface as well, and that will be a convective heat transfer. You can also have a convective heat transfer at the end. Okay, so if this is the at the end only, then you can implement that through a boundary condition, convective heat transfer boundary condition. But if it is through this surface as well, then you have to derive the equation, and finally, if you derive, then you will see that automatically T term will appear in the equation itself, and which is going to complicate because the stiffness matrix will not only come from this but also come from this component as well. Yeah, so accordingly you have to take care of it. We are solving the problem. Okay, and we start with 5.1. so there is a rod of 20 meters, and for that area is given, which is unit conductivity is given, which is 5 watts per degree Celsius per meter. Okay, and the uniform heat source, so Sx is uniform, which is given to be 100 watts per meter. Okay, okay, and then okay guys, in our derivation here we assumed S to be watts per meter cube, and hence we multiplied by this. Otherwise, if S is given in per meter, then you don't have to multiply here, so be careful with this. Yeah. Okay, now Sx equal to 100 watt per meter. Okay, the boundary conditions are T at x equal to 0 is equal to 0 degree Celsius, and Q bar at 20 is equal to 0 watts per meter square. Yeah. Okay. Now solve the problem with two equal linear elements. So two elements, and says linear. Linear, that really means two noded, right? Okay. And it says plot the finite element solution. So you have to find out what dth over dx. Sorry. Okay. You have to find out th and dth over dx. So these are the finite element solution, not the actual solution. And compared to the exact solution, which is, so exact solution is given tx equal to minus 10x square plus 400x. Yeah, so it's very easy actually, if you see. So how will you solve it? Now what you see here is a bar. So you have 10 meters here and 10 meters here. Yeah, so 20, and you are given that you have to use two elements of two node elements, right? So you have number 1 here, number 2 here. Yeah, node 1, node 2, node 3. Yeah. Okay, and then what? Then you have to, first of all, you have to find out what is the stiffness matrix. And in this case, what happens? You have, like you have EA over L, you have KA over L, and for element number 1, so we can write like this: K1, meaning was element number 1, is equal to E, right? Like you say EA over L, similarly it will be KA over L, right? Because instead of E we have K. Right? A is the unit, K is value is given, L is also given, and then you have 1 minus 1 minus 1 1, because this is for two noded, anyway you will get it. And this will also equal to K2. For the second element also you get the same thing, because there is no difference between the two. Exactly, you can get so big stiffness matrix K is usually KA over L, and 1 minus 1 0 minus 1 1, right, 0, and then you will have plus Now second one, when you write, it will be +1 here and -1 here, -1 and 1 here, right? 0, it will be like this. Yeah. So this is how it will be, the stiffness matrix. So it is done. Then temperature T is equal to T1, T2, T3, transpose of that, and T1 is given to be 0, right? It says T1 is 0. It's equal to 0, T1, T3. So done. Okay, now what? The force vector in this case, right? Okay. This is the, we say force vector, but in reality, this is the Q, right? The flux, basically. Okay. Now, when you say flux, flux is basically we are talking about the total, like watts per second type of thing. On a heat rate, we are talking about. Okay. Now, how to calculate it? So here it says the boundary conditions are given and a source is given, right? So source is given and S is equal to 100 watts per meter. Yeah. And then how do you calculate? If you are experienced, you know that if it is 2 noded and then you have S like this one, okay, and then total becomes S times L. So S, the length of the element is 10, right? S times L will be the total. It is a total like energy, right? Energy per unit time, that's in watts. So total Q will be given like this, energy generated, and half of it should come here, half of should come here. So in a way, if it is F1 and F2, F1 will be SL over 2, F2 will be SL over 2. If you are, that we have seen earlier, that's I'm saying that when you have to solve this problem in a quiz, this is how you will do, you know. Otherwise, if you want to go long way, what we will do? We will do S and then it will have N1. So F1 will be, first of all, F1 for the element number 1. So element number 1 is there. So F1, 1, right? So this is F1, 1, F1, 2 will be S N1 and dx and it will be 0 to 10, right? Which is equal to S is constant and N1, then you have S and then which is equal to this, this is 10 or basically it is L, right? So let's write L, L is this, okay? So 0 to L and then you have N1, so 1 minus X over L dx, right? And this is nothing, L over 2 simply, right? Which is equal to SL over 2. And similarly, you can get F12 as well. So basically, the total heat has to be distributed into 2, right? So half will go here, here. So you got it. Now, the second part also exactly same, right? It has the same S, it has same length and everything. Here also a heat generated, half will go here, half will go here. This number 2. So F21 is equal to SL over 2, which is equal to F22. Right? And hence F is equal to, what you will get? You will get, first will be F11, F12, sorry, F12 plus F21 and then F22, right? And which will be equal to SL, we can have L equal to 10, right? SL over 2, right? And then we have 1, 2, 1, like this. We have L equal to 10, right? So we can find out F is equal to, we found out already, yeah. So F equal to SL over 2, 1 to 1, where L is equal to 10. Remember, this is not the total length, this is the length of the element. Yeah, and then now do what? Now we have to apply the boundary condition, it says, right? And what is the boundary condition? And the boundary condition is that you are given Q bar. So we have applied T0 equal to 0, we have applied. But now you have to apply Q bar x equal to 20 is equal to 0 watts per meters. Yeah, watts per meter square. Okay, so this is given, and then we have to enforce that. Yeah, okay. So if this is given here, if the Q bar is given, what is the, how do you find out the Q bar? Q bar, as I discussed earlier, this is nothing but Q dot N. Yeah, and if it is an end, then N is nothing but I, right? So what do you get? You get is equal to, though here Q is directed outside here, so Q will be minus K dt over dx I. This is how Q is defined. Q is always directed in x direction. So this is if gradient of T is negative, then heat will flow in this direction. So this is what Q bar is. It is in I direction, and dot I, right? And that is equal to minus K dt over dx, which is given to be 0. Of course, it doesn't matter because here anyway it's 0, so sign doesn't matter. But actually, if instead of 0, if you had some positive number, then you would know how to apply this one. But it said that the slope has to be 0 at the end. That's what it tells you. But at the same time, you also know that here somehow this terms has to be 0. Yeah, although we have calculated like this one, but it has to be 0. So that means what? Our from Q bar. So Q bar is still in meter square. So we have to the F, right? What it tells you, F3. F3 is equal to Q bar times area. Yeah, you got it? So our F3 is a measure of the, if you see this side, the heat generation, how much heat you are getting, right? So did you see here, like we have X, then we integrated over length, and then, so whatever the heat is coming to the system, that goes at those points. Yeah. So here, what it tells you, F3 is what is the heat coming to the system. Yeah. And but this Q bar as such is the heat being lost. The Q bar is heat lost, remember, heat loss, because this is how, if Q bar is equal to Q times dot N, and if you see here, if Q bar is equal to minus K dt over dx, that really means that if dt over dx is negative, then Q bar is positive. Means if the heat loss is, if heat loss is here, then this term becomes positive, and hence Q bar is positive. So this gives you like this one. So F3 is nothing but you have to write minus Q bar A, because that gives you the heat gain, right? And that it is telling it to be 0. That is equal to 0. Yeah. So this term is 0 because here we have to enforce that equal to 0. Okay. So that term has to be 0. So okay. Now the final, what do we get? We get like this. We have Ka over L, and then we have 1, minus 1, 0, minus 1, 2, minus 1, 0, minus 1, 1. We get that. And then we have T1, T1 which is 0, then T2, then T3 is equal to right? And then we have SL over 2, yeah, and then which all things are there? Here, the first one, since temperature is fixed, we don't know what the Q will be, right? All the heat coming here, right? So although we calculated, so let's not write like this, we write like this. So although we calculated SL over 2, but there will be a reaction as well, so we write R1. Yeah, so we have to find out what the reaction is. Then second was SL over 2, so we'll write SL total, so we write like that. Third one, whatever we get, but we finally we get 0 basically. So we are putting that 0 because this is the final condition that has to be 0. Yeah.
So, sir, is it like the R3 reaction plus the SL by 2 is 0?
Yeah.
Sir, what is this reaction?
This is the additional heat. This is the additional heat that being. So you see, there will be two components. The total heat loss is equal to 0. That really means that the heat which is coming from S term, right? So the total which is coming from here and here all has to be equal to 0, right? So what is the meaning of this is that see here, we have S term here, right? So because S also, it produces some, it will also produce some, there are heat gain here, right? Got it?
So you mean there is a heat source, but it's making heat gain? Like heat gain will obviously be there. Like what is SL by 2 then?
So that's what I'm saying. So you can, okay, let me see. You can also understand by, let us say, since it's a heat transfer, so let's go here. So let's understand in terms of a structure, right? In a structure, what happens? In a structure, you have, let us say, like this, you have a body force like this one, right? Okay. Now, when you calculate here, this is a B here, right? B here goes like this. Yeah. Now, if you look at the finite element analysis, when you do, then what happens? You get BL over 2 here, BL over 2 here, right? You call it F1 equal to this you call it F2 equal to this.
Okay, and there is one reaction force also. Okay. Okay.
Yeah, you got it? So that means when you apply, when you say this has to be equal to 0, now because of this reaction force itself, I mean, whatever the 0 is, because of that, it is going to be added to it, right? Means this one is, there will be a reaction force as well in a way. So if you understand this one, automatically you will understand that also. So if you want to solve this one, how will you solve? You will solve like this. You will say A over L, right? And then say O1 minus 1, 1. And then you say 0, and we don't know what that is. So U2, you will say, and then what you will do? You will tell this one we don't know, although this one is BL over 2. So you write BL over 2 plus reaction R1, right? And second one is
0.
0. So 0 is coming from just because of these end conditions, right? So the 0 will be there, right? Plus we have to add this guy, this one. So this you have to BL over 2, you have to add it like this. Then only you can, that is the meaning of that, meaning that here at the boundary there is no boundary condition, but at the same time this is the body force which is the one which will be coming here anyway. From the outside it is not coming, but from inside this has to go there, no? So finally it will be like this one. So similarly here also you have 0 which is coming from the boundary condition, but we also have to write plus SL over 2 which is coming from the body force. You got
Okay,
it?
sir, got it.
Same condition. Okay, so now we have that. And then anywhere when you have a problem, always you can go to something that makes sense to you, because there is equivalent structural system here and you can relate it to. Yeah, so automatically you can go. So we have like this. In any case, you have to add all the forces, remember. So whatever the force coming from the boundary condition, that you have to add. If from the body force something is coming, that you have to add. You have to keep on adding, right? That's why we added this plus reaction as well, because reaction is coming from this boundary condition, so we added it. Originally we had this, so we kept it. That's how we did. Yeah, so we have to do like that. Okay, and rest is Ka over L, 2 minus 1 minus 1 1, T2 T3 is equal to, right? We have SL over 2. That's it. And then rest you can find out T2 and T3. Yeah. Any question, guys? Any question? Then you can, based on this one, once you have found out this one, you can find out R1. Yeah, and R1 will give you the actual reaction, right? R1 is the total heat. Total heat, it will be lost there, right? Total heat lost at the I will write gain only, because if you get minus, in this case you will get minus. Yeah, so what, because you have a heat source and somewhere heat has to be lost, otherwise it will cannot maintain temperature. So it will be, you get Q here, R1 is minus, so when you minus it will be lost basically, but R1 is the total heat gain. Let me write it at node 1. If you get negative number, that means it is losing. Yeah, any question, guys? Any question here? Okay. Now problem 5.2, it says that repeat 5.1 only, but with 4, 8 and 16 elements, you know, so you can use MATLAB to do it. Okay. Okay. Now problem number 5.3. It is again a heat conduction problem, and it has a unit cross section. So A equal to half 1 only. K is also given to be 5 watts per degree Celsius per meter, and linear heat source S. So what is the difference here is, it says that now it goes from x equal to 1 to x equal to 4. Yeah, and then it says the heat source goes like this. This is the heat source. Okay, and how it is, S is equal to 50 over 3 x plus 2. Yeah, this is the S. Boundary condition is given to be T x equal to 1 is equal to 100 degrees Celsius, and T x equal to 4 is equal to 0 degrees Celsius. Yeah. Okay, so both the it has U or T given at both the ends. Yeah, so you don't have to invert the matrix. Yeah, since T is given at both the ends, you don't have to invert the matrix then. You have to just find out Q both the places. So divide the bar into 2 elements. Yeah, as shown. Okay, now in that case you have to invert. If you have to find out the middle, what is the temperature here in that case. Okay, now divide the bar into 2 elements. So it's asking you to have 2 elements. Okay, divide the bar into 2 elements, and however as shown in the figure, and then it says that, okay, so element is like this though, so like this. Yeah, so element number 1, okay, element number 1 is this, element number 2 is this. It is also given this is equal to 1, then you have x equal to 2, x equal to 3, and so on. This is element number 1, this is element number 2. Okay, element number 1 is 3-noded quadratic element. Okay, so this is 3-noded, so 1 2 3 you have that, and then you have 2-noded element. Okay, and what it asks you is a strong form representing the heat flow and solve it analytically, find the temperature and flux distribution. First is telling you to find analytically. Okay, second is the construct element source matrices and assemble them to obtain the global source matrix. So, and note that the boundary flux matrix is 0. Okay, so what it is talking about is source matrix. When you say source matrix is nothing but matrix, but because of force vector F vector because of Sx is the source matrix. That's what we're talking about. Yeah. Okay. Then construct the element conductance matrix. When you say conductance matrix, matrix is nothing but the K or a stiffness matrix. And finally, you have to solve the problem. Finally, that is the thing. Okay. Now, how to go about it? First, you have to find out what is the stiffness matrix. Yeah. So now it is given like this one. So for three noded element, you remember how we did for the, so if it is you remember we had minus L over 2, doesn't matter actually. Once you, so we had total L, and for that, for the structural system, we found out K is equal to EA over 3L, and then you had 7 minus 8, 1 minus 8, 16 minus 8, 1 minus 8, 7. We had like this. So instead of K, instead of E, you can have K. That's it, right? So the rest remains the same once you, yeah. So K, and this K is which K? K1, first element, and K2 you have Ka over L, and you have 1 minus 1 minus 1 1. Only thing is we have to see the global one. So we have 1 2 3, and then this is number 1, right? Number 1 element. Number 2 element, we have 3 and 4. 3 and 4. So we can write here, this is 1 2 3, 1 2 3. Here we have 3 4, 3 4, and you can assemble them, right? Yeah. How will you assemble? We assemble here, like 7 plus 1 will go here, minus 1 minus 1 1. I mean Ka over L. So you can have K total K is equal to here. Let's have Ka over L here. Yeah, maybe we can have 3L as well here. That makes it easier. And then we have 7 minus 8, 1, 0. Yeah. Okay, we will see here actually, but it will be 0 only. So then we have minus 8, 16, minus 8. Then we have 1 minus 8, 7. Then we will have plus 3, right? Minus 3, minus 3, 3. Why 3? Because 3 is there, right? So multiply with this, it becomes k over L. Yeah. Okay. Only thing is we made a mistake. And what is the mistake? Our L here, this L and this L, there is a difference, right? So this one is L, and this is a small L, right? So let's say remain L, we call it L over 2, where L equal to 2, right? So that way, so L equal to 2, and we will have, in that case, our K, 2K over L it will be, because L over 2 will be here, right? 2K over L you will have. Yeah, because L equal to 2, because this L and this is L over 2, to be consistent, we are like that. So, what do we get? We should have here 2 here, right? And here, if you multiply 1, so we should have 6 here. Yeah, so let's multiply it by 2, by 2, by 2, by 2. So this is what it will be, Ka over 3L, the rest will be 0. Yeah, quickly let me write it. 7 minus 8, 1, 0, minus 8, 16, minus 8, 0, 1, minus 8, 13, minus 6, 0, 0, minus 6, 6. So where L equal to 2, remember, yeah? Okay, so stiffness matrix, how we get that? Now it says the S, T matrix or T vector is nothing but T1, T2, T3, T4, transpose of that, and okay, and only thing it says that T1 is 100 and T4 is 0. So where, or you can write equal to T1 is 100, write 100, T2, T3, and T4 is 0, so write 0. So this is T matrix. Now we have to find out F vector, right? And for that, F equal to, we will have, write Q1, Q2, Q3, Q4. You can write like that, transpose of that, and we can now calculate how they are. Yeah, there are many things that come here, as you know, right? So because of S components, so you can write due to Sx. Yeah, and you can have Q1, Q1, 1, and this is because of X. You can write also, write S here only, right? Just to indicate that because of this S1 will be equal to 0 to L, L is equal to 2, then N1 of element 1, X, right? Now be careful here, right? So here in your X is starting from, when we calculated, and I mean X starting X from 1 to that, right? So basically here we have to convert it into xi. So I think let me discuss that first. Okay, so what happens? Our S, always can remember this thing, yeah? Sx equal to 50 over 3 x plus 2. Now only thing is X varies from 1 to 4. Yeah. Now when we calculate the, you remember our 3-noded one, 3-noded, instead of X, let's call xi system, right? And our xi system had This is xi system, right? And this had xi1 is equal to minus L over 2. Xi2 equal to 0 and xi3 equal to L over 2, right? And we have N1 xi given as, do you remember? We had xi minus L over 2, right? And then we found, you put what, L square. Okay, you can put N1, let's say it was C1. So N1 at minus L over 2 has to be equal to 1 is equal to C1 minus L over 2 minus L. So equal to C1 L square over 2, right? And hence C1 equal to 2 over L square. So N1 xi is equal to 2 over L square xi minus L over 2. So this N1 is defined for this coordinate system, not for x equal to 1 to x equal to 4. You know, so there is a confusion here, right? So accordingly, we have to convert. So the same thing, we know that our x system, a xi system, our x system goes like this, and then our element is x equal to 1 to x equal to 3, first element. Our xi system we have to look at, and our xi system should be like this. Xi system goes minus L over 2 means minus 1, and has to goes to plus 1. Yeah, right? So that is xi equal to minus L over 2 equal to minus 1 is equal to xi equal to L over 2. Here, this one is xi equal to L over 2 is equal to 1. So there is a correspondence from x and xi system. There is a correspondence, right? And accordingly, we have to convert. So how do we do? So yeah, you can actually find out. So x equal to what? X equal to the difference in x1 means this value, you call it a and b, right? So this one is a, this is b. Same question you can apply. So x equal to you write a plus, and then the ratio of the two. So ratio here is b minus a divided by the ratio of 2 is, this one is 1 minus 1, so becomes 2. So this becomes 2. Yeah, and then multiplied by, then x here xi, we are writing in terms of xi. So then we have xi minus the minimum one, right? So plus 1. Yeah, it's fine. Which will come to be a plus b over 2 plus b minus a over 2 xi, right? This is how, because here also we have the origin here, like, so here this will add to this one, so automatically becomes a plus b over 2 like this, right? Okay, now is equal to a plus b is 3 plus 1 equal to 4. 4 divided by 2 is 2, so 2 plus, and again here 3 minus 1 is 2 divided by 2 is 1, so 2 plus xi. So we get like this. Yeah. So we have like this one. So s which given by 50 plus 3, x plus 2 will given by 50 over 3 divided by x is this, the 2 plus xi plus 2. This becomes 50 over 3, 4 plus xi. So sx becomes this. Now you can do it, right? So Q, because of the element 1 at node 1, is equal to minus L over 2 to plus L over 2, and then you have the S xi multiplied by N 1 xi d xi, yeah, is equal to minus L is 2, so minus 1 to 1. S we found out already, and which is like this, 50 over 3 plus 4 plus xi, so 50 over 3, 4 plus xi, so this is S, N1, N1 is 2 over L square, right? So L, where L is equal to 2, so here we have 2 over L square, where L equal to 2, so 4, 2 over 4, and then we have xi, then we have xi minus L over 2, where L equal to 2, so S xi minus 1, right? So this is N1, and then d xi, right? So then you have d xi, so you can write that d xi, again, that from dx to d xi we have to make. So here there will be something coming here, j here, right? So j times d xi, so dx see here. Yeah, okay. So we have this value x as this one, right? So our dx has to be, so dx has to be equal to d xi simply here, because x is equal to 2 plus xi, so dx equal to d xi simply in this case, d xi. So you can write d xi, there is no other thing required. Yeah. So this is how you have to convert, you have to be careful. That's what I mean to say. Yeah. Any question, guys? Good thing is it's already in this form, minus 1 to 1. So you can integrate numerically as well. You can use the Gauss quadrature. And hence, sometimes it's important to convert from X system to xi system. Yeah, this is the advantage. And the rest you will do, so only here, main thing is it is the same as earlier. Only thing is S is a function of X. And here the bottom line is S you have to convert into xi system. I mean, the shape function and S function has to follow the same coordinate system. Otherwise, there will be a problem. That's the takeaway. Rest you do it. Okay. So any question, guys, on this? Okay. I have not been able to post the homework yet, but I hope to do it by tomorrow night. Okay. So I've been very busy, so could not, but yeah. So tomorrow we'll continue with the homework. The tutorial anyway. Tomorrow there is no class. Okay. On Wednesday we will do the tutorial. Okay. Okay, guys. Thank you.
Thank you, sir.
Thanks, sir.
Thank you, sir.
Thank you, sir.